Hi, I'm Matt Larson with the HDF group, and today I'll be talking about the new multi-interface for the Highly Scalable Data Service. Before I get into exactly what that is and how it can be used, I'm going to start off with an introduction to sort of the existing ecosystem for using HDF5 through Python and your options in the cloud for doing that. Let's get started. So first of all, there's the absolute bedrock of everything. Obviously, the HDF5 library itself for working on HDF5 files on your local machine. But for people who don't like maybe don't like the C API or don't want to work in C in general, there's H5Py, which provides this nice Pythonic wrapper around HDF5 library operations, still using it internally, but providing a lot of nice stuff that data scientists find helpful, like NumPy-like indexing, and in general, just an easy-to-use API. So now, diverging from HDF5 files on your local machine, we have one option for working with them on the cloud, the Highly Scalable Data Service, or HSDS. And this is a web service which offers a REST API for, well, I said HDF5 in the cloud, but I should be more precise. It provides the HDF5 abstract data model and an HDF5-like API for storing data in the cloud. The underlying object storage does not match the native file format. And there's, the reason for that, because doing a one-to-one byte translation of maybe the entire thing as a blob into cloud storage into, a giant object is a native approach that's not going to work super well for most scenarios. And this talk isn't just about HSDS internals, so I won't go into too much detail about how it works internally, but I'll go over a few key features and considerations. One being that a major aspect of how this translation is done from the native file format to cloud and object storage is treating a single chunk in a data set as one object. And this enables a lot of useful behavior. But one way this comes in very handy is with large reads and large writes. These large requests that span, dozens or hundreds of chunks, depending on your use. HSDS's internal architecture in this diagram here has multiple service nodes and data nodes. And so when you have these operations on many chunks, HSDS separate data nodes can divide up that task into multiple pieces operating on disparate chunks, and then operate on them in parallel, because reads on those separate chunks cannot be done separately. The service nodes are slightly different, therefore handling many requests from potentially many different clients, because in many cases, the use case for this web service is exposing it to a lot of different clients. You might need to work on different files or the same files or read from them at the same time. I talked about cloud storage in the abstract without mentioning any particular provider, and that's because HSDS actually offers as an option compatibility with several different cloud providers, whether that's AWS S3 Bucket, OpenIO, or Azure Blob. Any of those can work with HSDS. Once you have this HDF5-like data stored in the web service, you have several different options for how to work with it. You can use command line tools that are provided as part of the H5PyD package. I'll talk about H5PyD in a moment. You can use the RESTful if maybe you're a C library user and you like using bool connectors. You want to keep using your C API programs, or you can use what H5PyD provides. Before going into how H5PyD simplifies this, let's look at just how you might use HSDS directly if you didn't want to use any of those other options. Like I said, it provides a REST API, which you operate on using HTTP requests to do, HDF5-like operations. So common operations like making a data set, that will be done through a post request to this data set endpoint that HSDS exposes. You make that post request, it goes to HSDS, it does the work on whatever backend is being used. Once that's complete, it returns with a 200 and provides you some information about that, information about the new data set, primarily the ID assigned to it by HSDS. IDs are used by HSDS to uniquely identify certain objects. And in this case, for a dataset ID, you can then use that to perform operations on the dataset, such as writing to it through making a put request to this dataset value endpoint. That value being an extension to the dataset ID. Another operation, just as an example, say you want to create a link to some existing object like a dataset. You want to create that link in some group. You would need the ID of that group created by a previous request to HSDS, and then make a put request with the information, such as the string, if it's a soft link, and make that request to this link name endpoint for the link you're trying to create. So okay, now we can go back and expand on that diagram for the kernel here. Obviously, I just followed up Alexander talking about cloud optimized HDF5. So obviously this diagram is, not an examination of every technology that exists, but now we can expand it a little bit to include HSDS. You want to do HDF5 like storage on the cloud. But odds are that if you're, someone, a data scientist working with Python, using the HDF5 data model, the odds are good that you're using H5Py. It's very popular. And if you're using it, that's probably because you like its interface and you don't want to go around changing things, rewriting everything you've already done to use this request-based infrastructure. And if that describes you, then you're in good company because the HDF group maintains and publishes H5Py distributed, or H5Py to solve this exact use case. You're interested in using HSDS, you're interested in working with the data model on the cloud, but you don't want to go in and change everything just for that benefit. And H5Py is sort of the mirror image to H5Py, as suggested by its perhaps slightly confusing name. In the same way that H5Py is this Pythonic wrapper around the HDF5 library, making it easier to use, but still using it under the hood. H5Py is a wrapper around HSDS. And the wrapping that it provides, the interface it allows you to use, is actually exactly the same as H5Py's. But those H5Py API operations are now going to be done under the hood as assembling a request to HSDS, sending it off, getting it back, and then unpacking HSDS's response into what you would normally expect as an H5Py user. So what does that actually look like? Well, let's say you want to make this transition. All you need to do is set up HSDS, and then as far as your pre-existing data management code goes, you simply import H5Py in the place of H5Py. It's a drop-in replacement. And so now these previous API calls you were making, let's say, creating a data set within a group, H5Py provides this nice interface to do that. Now that becomes a post request to that data set's endpoint. So H5Py will go through the work of translating that request with the parameters you provide into a request, send it over the network to HSDS. HSDS sends back that response, and it unpacks the relevant information and returns what H5Py was. One more example of how this is done. Let's say you want to write values, some array, maybe some list, to a data set. Again, that becomes the appropriate request. H5Py assembles this put request, sends it off to the endpoint, gets it back, and unpacks the result. So great, all right, this is awesome, right? Now you can just plug in H5Py, set up HSDS, and now you're on the cloud, and everything's awesome. Forever, nothing will go wrong. It's perfect, right? Well, no, not exactly. Maybe you don't have to think about the fact that you're now, working on the cloud, but you probably should. And one of the reasons that you should consider this is the small packet problem. Now, this is maybe a contrived example, or maybe not. But let's say the client who wants to read just one single element from a data set, and you're using HSDS to do that. Well, okay, you send out your request, travel across whatever network, gets HSDS, it gets that information pretty quickly, and now travel all the way back across the network, the client. So great, you got your 8 bytes, and you waited through 2 entire phases of network latency. And this isn't, ideally, your I/O would never look like this, but maybe you could get away with this on a local file. But now that you're working with HSDS, probably you can't anymore if you were before. So how can we deal with this? Well, one potential solution is batching. Maybe you still need to read just one element, but if you need one element from 50 or 100 different objects, you can mitigate this problem by batching all those tiny requests into a larger one. So let's say now you read one element from 50 objects and get all that back at once. So just by doing this, just by doing batching, you cut out, in this example, something like 98 instances of network latency, cutting out a massive amount of overhead on tiny operations. And so the 2 areas where this approach is used in the new interface are the multi-attribute and multi-link interfaces in the H5Py wrapper for HSDS. I'll start off by talking about the multi-link interface. Links are a pretty clear use case for this kind of batching because link operations, links are small, they're metadata, a soft link might only be, a string of maybe 100 characters. And a hard link is going to be an ID, which is, maybe however much space you need for one integer. And so by batching link operations, you can see a lot of gains in terms of eliminating overhead. Here's an example of what that API actually looks like in H5ID. Now, instead of this request at the bottom, it's very H5Py-like. This is what it would look like to create a link in that group using H5Py. But now these parameters are providing the indexing into the group and the value provided. Now each of these is a list of 100 elements. You have a list of the names of the links you want to create and a list of links. In this case, they're H5Py soft links to 100 data sets named, dset 0 through dset 99. And so now in this one request, you've made 100 links. And this multi-interface exists for all of the basic operations on link objects, not just creation, but also retrieving link information. So in H5Py, let's say you have some links in a group or one link in a group and you want to get information about it. The way you do that is with this group get function. Normally you would provide the name of the one link you're interested in with this get link parameter to indicate, you want the link information, not the object it points to. The multi-link extension now lets you say, okay, I don't want one link, so don't give me the one name, just say none, and now I'll go and get every link in this group. And again, we're talking about HDF5, H stands for hierarchical. Maybe you have some really great, really intuitive, deep nested group structure in your file or in your file-like data in HSDS. The H5PD interface also offers this follow links option to the group get function. So again, you say none, don't target one particular link, get link because I want that metadata information, and follow links. And so now within that target group, you're not just getting link information directly in that one group, but also information on any link, in a subgroup of that group or in a subgroup of a subgroup. So you can traverse this entire potentially very complicated hierarchy structure in a single request over the network. Whereas otherwise, you might say, okay, one request to go see what's in this group, one request to go get information on that particular group, just a bunch of requests piling up to traverse each little aspect of the structure. Now it's all done in one request. So what's the actual impact of this? Does this matter if you have a lot of links? So here are some results from a benchmark doing operations on 10,000 links. Comparing individual, create 10,000 links in 10,000 requests or retrieve information in 10,000 requests. And the effect here is, it's massive. You can barely see, like on the bar graph, how long it takes now with this new interface. It's something like maybe a 200 times speed up on creation and even larger than that on retrieval. So we can see that for these tiny, tiny objects in HSDS, most of the time you're spent waiting is on latency overhead over the network. So, maybe you don't have 10,000 links in your file. That's perhaps a pathological use case, but even for smaller amounts, you'll still see pretty worthwhile gains from using this interface. So, all right, that's the links interface. What about attributes? Attributes are different than links. They're somewhat data set-like. They can have a non-trivial amount of data associated with them, but they're still generally intended to be small, on the order of kilobytes. And so if your network latency is large, attributes are a case where, that latency is going to be a substantial portion of your waiting time, depending on your exact use case. So again, batching here can be very useful. So a brief overview of what this interface looks like in H5PD. Again, we'll look at creation. That involves setting up the names of the attributes you want to create and setting up all the values you want to populate them with ahead of time. In this case, let's say we have some attributes, each of which are 100 values, and give them basic name attribute 0 through attribute 99, and create them in a single request. This attributes create routine, again, exists in H5Py, but now in this new H5PD interface, it will also accept lists of multiple attributes to work on in a single request. Similarly, this routine is unique to H5PD, this get attributes. And again, that value is returned. It's going to be information, not just the metadata, but the actual, the values, the data associated with those attributes. Now, in one request, you can read all these attributes. So again, how much does this matter? And the answer is, depending on use case, potentially a lot. In this case, we say, what if we have 100 attributes, each of which is 1,000 integers, a somewhat reasonable estimate for a lot of attribute sizes. And again, we see pretty substantial order of magnitude speed up. Reading or writing 100 attributes goes from 2 seconds to a tenth of a second, 20x. And then retrieval is an even more substantial improvement from around 2 seconds still to the 1/20th of a second. So that's 50x, 40x, somewhere in that ballpark. So again, very substantial improvement with these tiny objects where most of your time spent waiting is going to be just dealing with network latency. So let's go back to the original small packet problem. So one way to mitigate this is, like we just looked at, batching with small requests. Are there any other approaches we can take to this that may be applied to different objects within an HDF5 file or the HDF5 abstract data model? Well, what if we try using parallelism? After all, HSDS can handle multiple clients sending multiple requests. So what if we have one program, act like multiple clients and send these small requests in parallel so that, even if it does have to spend some time waiting, maybe it can at least wait multiple times at once. And this is the basis for the multi-dataset H5PD interface, the third and final part of these new multi-interfaces. And this one looks a little bit different. This is implemented through this new multi-manager object. And the way the multi-manager works is that you instantiate an instance of it associated with a set of data sets to operate on. In this case, we provide it with 3 different data sets. Then later operations, such as reads and writes, are done on this multi-manager object in order to operate on each of those data sets in a parallel fashion using a different thread up to a limit of 16. So say you want to read from all 3 of those data sets using different threads, making different requests to HSDS. That's done through the normal NumPy syntax that H5 provides, that ellipsis selection, read from all of them, and then the data you get back, that'll just be a list where each element corresponds to the value read from one of those data sets. So that's reading, and writing works pretty similarly. Let's say you want to write, you have these 3 different arrays with different values you want to write to each of those data sets. You create this list of that data to write, and write it to that selection. In this case, we select all. But you can do unique selections on each data set in the multi-manager. This isn't the only use case of the multi-manager, though. They need not be unique data sets. Let's say you want to read from 2 selections in a data set that are in very disparate regions. Maybe you want 100 by 100 area near the origin of the data set, and then 1,000 by 1,000 area somewhere way off at 6,000. You can do that with the multi-manager and optimize that operation by setting up NumPy slices, bunching them up in a list, and then providing that list at the time you do the read from the multi-manager. And again, this is done in parallel, 2 different threads, 2 different requests to HSDS. So how much does this matter? And the answer is, it's still pretty substantial. So these first 2 benchmarks here are areas where we tried. Okay. These first 2, full read and full write, we're saying, we have 64 data sets of some non-trivial size, and we try and just, throw them into multi-manager and replace what we were doing before. How much does that get us? And the answer is about 50%. So pretty good, but not, the order of magnitude improvement. But where the multi-manager really shines is in use cases similar to the multi-attribute and multi-link interfaces. Maybe you're doing random accesses of somewhat smaller size, maybe 5% of your data set in some random pattern. And in that case, again, where latency rises as a relative concern, doing this using multiple threads, multiple requests is going to have a substantial impact, something like around 10x in that case. So that's the new multi-interface. And before I wrap up and take questions, I'll go over a few closing remarks if you're interested in using this, and a few words of caution on how to use them appropriately. One is that these are new interfaces, and while they are implemented and being tested, they're in a workable state. They have not yet been published in an official HSDS or H5PD release. So if you're interested in using them, you for now will need to build from source, but we hope to get them out in release versions soon. Another note. So I talked about how the whole point of H5PD is that it provides this H5Py-like interface. And now we have this extension, which obviously isn't an H5Py because H5Py doesn't have to worry about optimizing for the cloud. It's for local files. So, some of the things you change here might impact reverse compatibility if you move back to H5Py itself for local files at a later date. That being said, H5Py does have some things in progress. Notably, it has a multi-manager in the works, which is implemented differently internally. It uses the library's own multi-read and multi-write functions, but it accomplishes the same fundamental goal of operating on multiple data sets. And it's likely to provide the exact same API as H5PyD's multi-manager. Another option for dealing with multiple data sets with HSDS particularly is the RESTful. I mentioned this a little bit earlier, but if you're a library user who wants to use full connectors and you're interested in cloud storage, the RESTful lets the C library itself deal with files stored on HSDS. And the RESTful offers compatibility with the library's multi-read and multi-write to do something similar to the implementation you saw here. And then the last sort of word of caution is that the multi-manager for data sets, it's not a free lunch. At the end of the day, HSDS is constrained by the resources it's initialized with. And so if you send off, 100 requests to go read these massive data sets, eventually HSDS is going to reach its capacity. It's going to be completely busy and say, give me a moment to finish this and send back a 503 request. So multi-manager, in terms of reading large data sets, it's best thought of as a way to make sure that HSDS is fully utilizing the resources you have available to it. All right, here are some links to relevant information on the programs I discussed today, HSDS and H5ID, as well as a link to the HDF forum talking about HSDS, where you can see questions other users have had and find some relevant information. All right, thanks for listening. I guess if anyone has any questions, I can take those now.
Cool. It's nicely implemented in Python. It's all cool that way. Especially for the link interface. If I had a 200x improvement with the special fuzzy wuzzy, man, I'd make that the default. Just put it in there and do it the default way and leverage it forever. Don't make the users beg for 200 times improvement in performance. Just do it all the time. Attributes, marginal, data sets got weird special cases, but man, the links look like a huge win for a default.
I think, just off the top of my head, my thoughts on that would be, it would be great to do that, but, H5PyD can't magically know a user's future intentions. Maybe a user wants to make one link and we should just go do it. We can't, maybe we could try caching requests they're going to send, but we're not going to know their future plans to make 10,000 more links right after this.
Been there. But 200x takes everything. Just do it.
That.
Hey, Quincy?
Yeah, sure. Hey, John.
Hey, yeah, there actually is a property for the H5ID file open that downloads all the links and all the attributes as part of the file open. But you can disable that if, for example, the file is like really large, and then that HSDS and the file open will spend a lot of time iterating through all the links and attributes and such. And another use case is that you are writing a multi-reader, multi-writer application, in which case you want to have the current data for a link or an attribute, not what you cached at the initial file open.
Sure, very, really good use cases. But I mean, I do the cloud programming thing already by this point too. You've got a lot of resources. You're idle most of the time. Progressively send them, oh, here's the first batch that I could get in a reasonable period of time, chug away into the background, and then the next interaction you have with a client, or even asynchronously push it to the client and say, and here's the rest. Easy to do that. And the other way, then you refresh, right? Oh, here's the delta, here's the changes. In the same way, here's the rest, right? It's just a delta update on what I sent you before.
Yeah, that's an interesting idea.
Good.
One more question. It looks like the more questions. Thank you, Matthew.